Welcome back to PPT. In this video, we are going to focus on minimal sets of FDs. Very simple concept. So let's just dive right in. Minimal set of FDs. Yeah. So whenever we are speaking about minimal set of FDs, or we can say minimal cover of FDs, minimal set of FDs, or you can say minimal cover of FDs. If you have a set like set of functional dependencies F, the minimal set of F, the minimal set of F is simply denoted by the notation F dash, or some people call that as F prime or F complementary, whatever it is. I just call it F dash for my easiness. Okay, for my easiness, I call it F dash. So let's continue. So there are three key characteristics of a minimal set. The first characteristic is single attribute on right side. Single attribute on right side. Okay. Now you have to be very careful. This is not single set of attributes. It is single attribute on right side. It is a single attribute on the right side. So every FD in a minimal set of FDs, every FD in a minimal set of FDs, has a single attribute in the RHS. Has a single attribute in the RHS. Okay. For this, I'm going to take an example. I'm going to show you an example. So let's use a table for that. Okay, let's use a table. So we have a relation called relation. Let's say relation. And let's say there are something like student number, and we have student name, and we have student age, and we have student age. Yeah, this is it. Let's say this attribute is X, and this attribute set is Y. You can simply say X functionally determines Y without any issues. Okay, so let's say that is F in this case. F X functionally determines Y. So my question is, what is F dash? What is F dash? If you said X functionally determines Y is F dash, you're wrong. Okay, you have to be clear about that. I already told you the first and foremost characteristic of a minimal set of FDs is the right side should have only one attribute. Y is equals to two attributes. What are those? Student name, comma, student age. So this won't work. So you have to mention let A equals to student name. Let A equals to student name. B equals to student age. You can say like that. Okay, you can say like that. So now we know Y is equals to AB because A union B is equals to Y. That's why. So I can use, we can't say Y equals, we have to say Y functionally determines AB. Y functionally determines AB. By using the decomposition axiom, I can say Y functionally determines A, Y functionally determines B. But the cute part is we already have X functionally determines Y and X functionally determines Y. We can use it again. So by using transitivity, we will get X functionally determines A and we have X functionally determines B. So F dash will be equals to, X functionally determines A, comma, X functionally determines B. Or you can completely skip this. And say Y functionally determines student name, student age. Okay, you can say this. So you can directly use instead using some specific set of letters. Okay, that can be redundant. So you don't have to show that. If you wanted, you can directly say f dash will be x functionally determines by using transitivity. Obviously, x functionally determines student name, comma x functionally determines student age. Now I can hear your doubts. Isn't this too much? Isn't it inefficient? Well, when we are speaking about minimal set of FDs, we are not thinking about efficiency. Now we are speaking about the techniques. Okay, minimal set will be useful in some other context in the future that we don't know yet. So for now, just keep in mind the minimal set, the first characteristic of minimal set is on the right hand side, only one attribute. Only one attribute. You can't have a set of attributes. You can have only a single attribute. That's the first characteristic. Now we are going to the second characteristic. Second characteristic is named as irreducibility. Irreducibility. Well, as the name suggests, you can't reduce the FTs in a minimal set. Okay. In a minimal set, of FTs, you can't remove, okay, we can't say you can't. In a minimal set of FTs, any FT can't be removed, without altering the closure set. Without altering the closure set. Without altering the closure set. Well, I will use another example for that. Let's say f is equals to a functionally determines b functionally determines c. Okay. So what is the minimal set of f here? What is f dash? Well, f dash is also a functionally determines b and b functionally determines c. Well, I will explain it why. Let's say b is single attribute. Okay, b is a single attribute. Okay, keep that in mind. B is single attribute. Also, c is single attribute. Keep that in mind. Or else this won't be a minimal set. Yeah, according to the first characteristic. So f is equals to a functionally determines b, comma b functionally determines c. So I am saying f dash is equals to a functionally determines b and b functionally determines c. Why am I saying that? Let's find out f plus first. F plus is equals to a functionally determines b functionally determines c. So I can apply transitivity and say a functionally determines c. I really like transitivity rule, you know. I really like that. By let's say you have a friend. Okay, let's say you have a friend named Abhi. Let's say you have a friend named Abhi. Let's say your name is Mitra. Okay, let's say your name is Mitran and you have a friend named Abhi. And let's say Abhi knows someone called Siddharth. Yeah, Sid. Let's say Sid. So since Abhi knows Sid and you know Abhi, you can go to Sid's party and say you're a friend of Abhi. Okay, so this is fun. Transitivity is fun, you know. Transitivity is fun. That's why I like transitivity a lot. So coming back to the topic, f plus is equals to a functionally determines b functionally determines c. By using transitivity of these two functional dependencies, I can say a functionally determines c. If I remove any one of these, it can be this or this. Let's first of all remove this. If I remove this, what will be f plus? Well, f plus will be b functionally determines c. Why is that? Well, you can't derive anything without a functionally determines b. You can't derive a functionally determines c. So this will alter f plus. Therefore, I can say f itself, is already a minimal set. Okay, f itself is already a minimal set. So I can't reduce any ft. I can't remove any ft. That's the story behind this. Now let's go to the third characteristic. That is non-redundancy. That is non-redundancy. Non-redundancy. As the name suggests, you can't replace an FT. You can't replace an FT. So any FT can't be replaced. Can't be replaced with a simple FT. Okay. So in a specific set of FTs, let's say if is equals to A functionally determines B and B functionally determines C, etc., etc. Okay, so in this specific set of attributes, any FT, okay, whether it is this or this, any FT can't be replaced with a simpler FT. Okay, so it can't be replaced with a simpler FT, which is a proper subset of original FT, which is a proper subset of original FT. Okay, how can you understand this? Well, proper subset of original FT without altering the closure. Okay, that's the third characteristics. So characteristic. So without altering the closure set of FTs. Okay, so let's say F is equals to A functionally determines BC is there. Okay, we can actually decompose this and we can have simpler FTs like A functionally determines B and A functionally determines C. This is a proper subset and this is also a proper subset. At the same time, this is a simpler FT and this is also a simpler FT. Okay, so I can actually replace this and I can say F dash is A functionally determines B and F dash also contains A functionally determines C. Okay, so this is what the non-redundancy is. Okay, so if there is something like this in the FT, we can say this is not the minimal set. This is not the minimal set. Okay, this is not the minimal set. Why? You can actually replace an FT. Okay, you can actually replace an FT with a simple FT, which is a proper subset of the original FT. But here you can't replace that with a simple FT. Why? A functionally determined B is the simplest you can see. A functionally determined C is the simplest you can see. That's why the third characteristic is important when we are writing or when we are focusing on minimal set of FTs. Okay. So when we are talking about a minimal set, yeah, when we are talking about a minimal set of FTs, we have understood the main three ideas. Yeah, the right hand side should only have a single attribute, and it should be irreducible, and at the same time, it should be non-redundant. Okay, it should be non-redundant. These are the important three characteristics that set of FTs has if it is a minimal set of FTs. Okay, yeah. So we have finally finished the formal guidelines also. Okay, we have finally finished the formal guidelines. Everything that we have to know to find the functional dependencies, to simplify and find the candidate keys are finished. Now we are going to focus on normalization in the upcoming videos. So yeah, stay tuned and let's see in the next video. Thank you for exploring minimal sets of functional dependencies with us. If you found this video helpful, give it a like and share it with your friends. Subscribe to the channel and hit the notification bell to stay updated with more videos in this series. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.